I will be talking about looking a bit beyond what we have seen. We have seen how we can structure data in relational databases using tables and columns and also standards how to preserve them. We will look a bit beyond because there are other forms of storing data. At the same time, I would like to argue that there is kind of an opportunity of a revival of ontologies to be used to preserve databases and other types of databases than relational databases, especially in light of new technologies that will transform, I think, the way how we work with data and how we preserve data. So let me start with a picture. The shelf, we like order. In this shelf, we know where we can find data. You see the wine glasses that are in one slot and music boxes in other slots, etc. Vinyl plates. So you find everything in a slot, but this structure is quite rigid because you know that sometimes with information, you think that, oh, I have some information here that belongs to two slots. What do I do? So you have to handle cases where maybe the structure does not fit the needs, and you have to get around that. So the order of relational databases has big advantages. It's used since the 80s at least and has become the predominant standard using relational database management systems. And there is SQL, which is a big advantage because SQL is standardized. You see the ISO IEC 9075 with all the SQL variants that belong to the standard. And so you have a quite a stable fundament to base the eArch, for example. The eArch specification is based on this and can rely upon a very stable fundament. On the right side, you see the well-known Northwind traders database from Microsoft that was available in Access and shows a schema where you have the definition of the tables and the relations between these tables in an entity diagram where you have the 1 to n relations between the foreign keys in the tables and so on. And so that is what we are used to work with and what the eArch specification basically uses to then rely the standard upon. So eArch has a specification for it, which you see redly highlighted on the bottom left. It's eArch. This is the specification, and out of the guidelines you see on the right side an example of a folder structure, specifically in this case related to the Northwind sample database, where you see the layout of how this database is typically archived in a eArch information package structure in this case. So, but sometimes things just don't fit into the schema. That's why to understand the complex world, we have a brain, and in this brain we have a structure that is well apt to actually capture very complex scenarios. And what do we do if we can't fit the real case into this structure? There's a downside of the order, which is schemas are strict. So every piece of information, you have seen that in the shelf, it needs to fit a predefined structure. You have tables, columns, data types, and data type constraints. On the right side, you see an example of such definitions. And whoever was involved in developing applications knows that schema changes are painful and are even more painful the more you advance in the development of the application. At the end, somebody comes, oh, we have to change here the relationship type between this entity and the other entity, and the other developer cries and says, no, 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 not at this point in the project, so please. There is this Agile manifesto. It came up in the 80s as well, which the developers were well aware of this problem of having these changing requirements. And they say, well, welcome changing requirements, even late in development. So that's just showing a bit how this pain of changing data schemas is. Then we have also the problem of scaling. Databases are different nowadays. We need to think about you have heard here from the Danish National Archives about petabytes of data. That is now an order of magnitude that we get quite used to. And vertical scaling is very expensive. So that is basically adding more power to a single server, and that has physical limits and is very expensive. There are different types. If we try to order a bit the limitations that classical relational databases have, we have the mentioned rigid schema, so it's not flexible. We have join limitations, so some complex relationships we are not able to actually cope with the joins that we use in the databases. We have seen one example of such a query before. We have scaling limits because the database as such is then not unable to cope with big data needs. There are OLAPs that cope with that to some extent, but still scaling these databases is very complicated. And if we look at the evolving landscape of data storage, we see on the top left the relational databases with some examples. The databases mentioned, they are not representative. It's just to have some examples. And you see the dots that show that there is much more to follow. Apart from the relational databases, there are distributed, cached, document store, graph, distributed key value, wide column key value, embedded key value, search engine streaming, time series, columnar, real-time OLAP, etc. So this is basically the tip of the iceberg. And also underneath you see that each of these categories has much more of types of databases below that. So it's an exploding landscape of data storage solutions, each of them covering specific needs. If we pick out some of the examples, we have the graph databases where we can, basically it's based on the nodes and edges. The edges are arrows that go from one node to the other node that show there is a relation. You can have in such a graph also properties of nodes, and you can model that. There is NoSQL, which is one form of it is to store documents in JSON format. It's very flexible. It can even be schema-less. So you have no schema, you just store the documents and have then a query language to query against these documents. As it has no schema, it has also disadvantages because you can't rely upon certain properties to be in your database, but there are also ways to get around that. On the right side, you see an HBase example, which is a bit more complicated because you have column families with the different properties underneath. So think about the landscape of solutions, then you see that you have a very wide variety of formats that you need to understand. And it's not as easy as before that you just rely upon SQL and look at that standard and understand that standard, but you will have a wide variety of formats and ways to store the data that you need to understand. Also the entities, so really at the core level of these databases, it's quite different. So structured databases, if we just pick these three examples, then you have different entities that you look at. At the left is the relational with the tables, rows, and columns. We know that. In the middle, we have the document NoSQL, which has collections, documents, and key value pairs. And in the graph, you have nodes, edges, and properties. So all of these types, the entities even change how we relate to the data and how we call things there. Here, for example, on the one side, we talk about tables. On the other side, we talk about collections. If we pick out one example to go a bit in the detail what preservation would mean for a non-relational database, we have HBase. as a distributed, scalable NoSQL database built on top of Hadoop and HDFS. We have in the E-ARK consortium a bit of experience with that because in the original project E-ARK from 2014 to 2017, we actually developed a prototype based on HBase that was able to demonstrate that you can store E-ARK information packages in this distributed large-scale storage. And the Hungarian National Archives had a prototype demonstrator for that. So HBase comes with a built-in MapReduce job called export. So if you think about, okay, I need to preserve this database, the first thing is to somehow get it out of the system. The possibility would here to dump the data, so-called sequence files, and you archive the sequence files. Now, okay, who understands sequence files? Not everybody does, so you have a problem maybe. What is good is you can use these sequence files to re-import them into a HBase database if the format remains compatible. That's good. But the sequence file is a binary and is tied to Hadoop, and it requires HBase or Hadoop in the correct version in the future. I don't know, in 10 years, in 15 years, how does that look like? We have no schema metadata, just rows and columns. So we can conclude actually that raw HBase exports may not be future-proof for preservation. We have technical challenges with migration. For example, it might be necessary to have intermediate migration, so-called hops. We need to transform the data. We cannot just go from the old database to the current database, but we have some intermediate migrations. And then the questions comes up, do we have the versions of the database management systems, the difference that we need to actually go to the new system? Do we have the licenses available? So a lot of practical challenges there. And then there is one of the key points I would like to highlight is that digital preservation is not only about formats. So on that side, to preserve the sequence file and somehow get it into the new system, we have achieved to get the format in the new system, to get the binaries again. But then keeping bits and formats intact is necessary, but not sufficient. A future user must still be able to understand the digital object as intended. The OIS model also talks about independently understandable by the designated community. So we must understand the data. On the one side, there is context, which is key for preservation. So just as one example, as environment data might be very important in the future because people want to know how we messed up nowadays the climate. So imagine an air quality monitoring system storing data in HBase, and we have sensors that log timestamped readings for particulate matter, just as one example, temperature, humidity, and location metadata. And you have that in HBase. So context means here that we actually understand what do the columns mean, and how they relate to each other, what is the documentation, and how do we document all that? And what happens in 5, 10, or 15 years? Can we still interpret or reuse it without structure, context, and preservation? We risk losing insights. So structure is key, and here is now, I come back to my initial statement about ontologies, because if we have ontologies, we have a way to structure the documentation, not just creating a PDF document where we document everything, but create a structure that shows what is a sensor that does the measurement and what is a pollutant type, what is the city, and how they are related to each other with the bubbles on the right and left side, documenting what these actually mean. So now, what is the advantage of having that? We have, and no talk without mentioning AI, so I promise that. So what can an AI do? But if you have that structure, if you have a PDF document, you need a human will read it, and nowadays also artificial intelligence, LLMs, they are capable of actually extracting information from them. But it's actually better to have reliable structures that you have. LLMs can use these ontologies if you create them carefully and and take care that everything is correctly represented in these ontologies, you can understand the relations that LLM can understand that data PM25 and data temp are instances of a measurement tied to a sensor entity and must be preserved with units and context. There is a data transformation, so LLMs can use that and help us mapping the flat H-base entries into JSON-LD or RDF. We can create human-readable summaries, export plans, queries, so for Sparkle, Cypher queries, technical details. So any downstream task, LLMs can actually help us if we provide the structure to do so. E-Archiving has a vision for that. If you see these inverse pyramid, which I have shown before, we are at the moment very much looking at the structural interoperability, which is the bottom of this pyramid. It's the less complex one. Still, it's very important because this lays the fundament, the basement of the whole building that we need to build, and we want to go up to preservation descriptive linked data. You see that with associated standards that we need to look into, and that's why I'm here stating that ontologies would be an opportunity to help us managing the relationships between these 4 different types of databases that are not only relational. So to boil it down to the options that we have, the first one is we just lean back and focus on other activities, as the guy on the left side who does some belly massaging, I think, using this machine. And we let the AI do the work. We have just our input text field, and we say, please do anything necessary to preserve this database information package. And then we lean back and hope that it will do everything for us. I think that's a dream. I think it will not come true. I think option 2 is the thing we should do, which is lean in. That is actively guide digital preservation using domain knowledge, specifically create ontologies. So tell exactly what you think is the right structure and what are your thoughts, what are the relevant entities, how would an application be running based on this. All the details you can actually document and preserve in this format. And then we would be able to make, to steer digital preservation, and in the text box we would say something like, given the structured database object and the included ontology that defines the entities and the relationships, etc., what is the recommended long-term digital preservation strategy? Because I think LLMs and AI in general may help us a lot doing digital preservation in the future, but still there should be some way to actually actively guide that. Thank you for your attention, and if you have any questions, thank you.